Thanks very much, Freddie, for inviting me here. It's such an amazing place. I've never been here before, and given that I love mountains and skiing, this is quite a venue. So I'm going to tell you about giving you an overview of research we've been doing for quite a while on sea ice and its role in the climate system. But I'm going to focus, given that the topic of this summer school is about fluids in the climate system and turbulence. I'm not going to talk too much about turbulence per se, but I will. But most everything is centered somehow around fluids. And I've actually never shown this photo before. This was coming from Europe over back to the United States, and you sort of often skirt Greenland. And I've seen this feature before. So that's Greenland. This is like the southeastern coast, and this is sea ice, and it was a beautiful pattern. And I'm certainly interested in these kinds of problems where you maybe track a particular flow and it's kind of a basic Brownian motion on small scale, but also it's being advected in larger flow fields. And I will mention some things about that later on the talk. But first, I'm going to give you a nice overview of sea ice and its role in the climate system and some of the work that we've been doing. Okay. So what are we talking about? We're talking about the cryosphere, the frozen portion of Earth's surface. And in the south, in the southern cryosphere, we have the Antarctic continent. There's the South Pole right about there. And these are, of course, the great land ice sheets that are 2, 3 miles thick or so on. But what we're interested in is the frozen seawater, the frozen ocean surrounding, say, the Antarctic continent or the Arctic Ocean. You'll see lots of images of that as well in the north. And as a professor of mathematics, I've been extremely lucky and a bit unusual in the sense that I've been to Antarctica now, I think 7 times, and the Arctic 11 times to do field research, to do field experiments on the sea ice, and you'll see a lot of results that we've obtained in the field, in addition to, of course, all the mathematical modeling and so on. And I started off over here first couple times when I was in college, and then as just when I got tenure in math department over here in the Weddell Sea. I've been in the Ross Sea down here, and I've been with the Australians 4 times over here off of the coast of East Antarctica. My first time with them, the ship caught fire. It was quite an experience as a math professor. It's like I prove theorems for a living. What am I doing on a burning ship in Antarctica? But okay, obviously I'm here, so we survived. So why study sea ice? Well, it is melting, but there's a lot of it. It covers roughly 7 to 10% of the Earth's ocean surface. It forms the very thin frozen boundary layer. By thin, I mean a meter, 2 meters, 3 meters in that scale, not not 5 kilometers like a thick ice sheet. As I said, it forms the boundary between the 2 principal geophysical fluids on the Earth, namely the ocean and the atmosphere. And as such, it mediates the exchange of heat. Here you see heat rising up with moisture through. This is actually the lifeboat that I almost wound up on of the Aurora Australis, the Australians' main research icebreaker. And so it mediates the exchange of heat, gases, momentum. Like if the winds push on the ice and it's very rough, it's going to drag the ocean along. And so there's these kinds of issues. And both the melting and the freezing of sea ice play a major role in global ocean circulation. It's one of the main ways that the polar regions communicate with the rest of the world's ocean system. In other words, sea ice has long tentacles that extend throughout the ocean system. And not only is sea ice a very sensitive indicator of our changing climate, but it's also a key player, an active participant in our climate system. And one of the main jobs that sea ice does, one of the main roles that it plays, is in reflecting incoming solar radiation during the polar summer. And this is measured, of course, by the albedo. And so whereas white snow and ice reflect most of that incoming solar radiation during the polar summer, seawater or ocean and in particular, meltwater sitting on the surface of white sea ice, that absorbs most of the incoming solar radiation. So here you see a classic white polar ice cap reflecting most of the incoming solar radiation. But then, of course, if you start losing that white polar ice cap, then it's replaced by darker absorptive surfaces, which then tend to absorb that radiation rather than reflecting it back into space. And of course, that's the issue. Is what's happening, is that we're losing that white polar ice cap and covering the Arctic Ocean. And so this is basically sort of the long, over 20 years, the average, about 7 million square kilometers. That's the minimal extent during September. So we're actually getting pretty close to that in about a month or so in terms of the low for the season. And so you see sort of over a sort of a slow fall off, and then things really got going around the turn of the century. And then that was the year 2007. That's when this started really entering into the media, and the news was being followed because it was a dramatic new record low. We sort of bounced around. In 2012, we hit a new record low. I'm not sure what will happen this year. It should be interesting to see if we're there. But on that, I remember that day. It was September 14th. It was the day before we were leaving for our 2012 SIPEX 2 Antarctic expedition. You'll see a little bit of footage of that later. But the extent on that day was about 3.4 million square kilometers. So we can all do the math. From 7 down to about 3.4, you can make the rather dramatic statement that we've lost over half of the summer Arctic sea ice pack, not in thousands or millions of years, but over this relatively short period. To put this in some geographical perspective, the area in red is what we've lost, at least in the year 2012. And of course, part of the issue is that, again, that white icy surface, reflective surface, is being replaced by darker ocean. So that darker absorptive surface is now absorbing solar radiation into heat instead of reflecting it back into space. And this melts the ice back, tends to melt the ice back further. And so it feeds on itself. And this is called ice albedo feedback, which is one of the dominant mechanisms that's helping to drive the precipitous losses that we've been seeing, particularly in the Arctic. Now, this is a somewhat old figure. This is the runs of the IPCC models from the fourth assessment about 10 years ago, but it kind of motivates what a lot of people have been doing, a lot of the work that's been going on in the sea ice world, and some of the stuff that we've been doing. And so, of course, these are the world's best global climate models. There's the mean runs, and whereas all of these top climate models predict a general decline of the extent of summer Arctic sea ice, none of them were able to capture the tremendous rate at which the ice was actually melting. And so this leads to a fundamental challenge. How do we represent sea ice more rigorously in climate models? It certainly 10, 12 years ago, it was represented in a relatively rudimentary fashion. How do we account for key processes such as the evolution of these ponds on the surface of sea ice? It's an iconic feature of the Arctic marine environment. And there's been some very enlightening simulations showing that if you include melt ponds versus not including melt ponds, if you include them, you get a September ice volume about 40% lower. So this is not, as mathematicians would say, it's not an order epsilon effect. It's order 1. This is serious effect. And there's other so-called subgrid scale structures and processes that we need to that we would like to incorporate into these so-called coarse-grained climate models. But there's a fundamental problem, and this is really sort of where I come out of. My background is in composite materials, although I kind of got involved in that by studying sea ice at NASA when I was in high school and then in college, and that led me into studying composite materials at Courant Institute for my PhD. And then homogenization and statistical physics. And so there's this fundamental issue of linkage of scales. How do you take information that you have about a system at small scales and then want to rigorously compute or estimate or analyze what the effective or overall properties are? And this is a particularly challenging issue for sea ice because it exhibits very interesting composite structure on so many length scales, starting over about 10 orders of magnitude. So when you freeze seawater, you can't incorporate the salt into the crystalline structure, and so it tends to reject the brine, but what's left is these tiny sub-millimeter scale inclusions of very salty water. There's algae that lives in there. One of these little things is like a little world in itself. It's fascinating. Of course, sea ice is a polycrystal. You can't really even see the brine inclusions. They're on a much smaller scale here, but this is the polycrystalline structure on the centimeter scale. And one of the things that that I am so fascinated with and have spent a good chunk of my career looking at is how the brine phase goes from disconnected inclusions when the ice is cold to when it warms up to forming long channels, like meter scale channels through which fluid can flow. Here's pancake ice forming in a wave field in the Southern Ocean. I'll talk a little about that later as well, some of the math that we've done recently. And again, I view this as a two-phase composite, and you'll see that very explicitly laid out in some work we've been doing recently on wave propagation through the ice pack. And so this is a two-phase composite of these little pancakes and the frazzly stuff that's between them. Again, moving up in scale, meter scale flows, bigger, sort of much more consolidated ice pack. Kilometer scale flows, that's the Aurora Australis, this ship I just mentioned. So it's about the length of a football field. And then again, looking from space, again, a time evolving two-phase composite of sea ice flows and ocean. Okay, so in a nutshell, what this talk is about is how we're using the mathematics of composite materials and statistical physics to study sea ice, its structures and processes, ultimately to try to improve our projections of climate change and the fate of Earth's ice packs. And the underlying theme here, probably the biggest single takeaway word, I've heard it once this morning, is homogenization. This is sort of the field of mathematics and physics that I kind of come out of, more particularly for composite materials. But it's really a formal area, I'd say, of applied mathematics, and I'll say a lot more about that as we go. So first, I'm just going to give you just a touch about climate modeling in the polar ice packs and say systems of partial differential equations. So the blue is kind of the mathematical topics that we're going to touch on. As I said, I mentioned the sea ice microphysics and fluid flow through this porous medium involving diffusion processes, percolation theory, and so on. I'm going to mention a little bit about how we monitor all these processes with electric fields, although that's kind of a ruse. It's not. I don't really want to talk about that. It sort of lays the groundwork for these other problems, the methods that we use, and in particular, of interest to you guys here, would be the advection diffusion problem. We've seen a fair bit of that this morning already. The polycrystal problem and waves in the marginal ice zone. And then I'm going to close with going back to these melt ponds and some fascinating things we've discovered about the geometry and transitions in geometry, fractal geometry of the melt ponds, and a lot of statistical physics models that we've been developing to try to understand the geometrical characteristics and the evolution of these ponds. Again, another couple of takeaways from the talk I'd like you to keep in mind are critical behavior. Certainly my background is in statistical physics, phase transitions, these kinds of things. And what I mean by critical behavior is you make a small change in a parameter of a system, and then you can induce very large changes in the overall or effective properties of the system. And that's, of course, inherent when you're talking just about water and freezing, just change the temperature slightly. And that's just one simple example, but I'll talk about more examples. And one concept that I particularly like that I think illustrates the power of a mathematical approach, and that is what I call cross-pollination. And you'll see a number of examples of this where we take mathematical methods that seemingly completely unrelated fields, but the underlying mathematics is the same, and so we can bring it to bear on sea ice, or take methods and ideas that we've developed for sea ice and apply them to, again, seemingly completely unrelated areas of science and engineering. Okay, so just a few words about global climate models. They're systems of partial differential equations derived from, of course, the basic laws of physics, chemistry, and fluid motion, and they describe the state of the climate system and its various components. And here's kind of the rub, is that these equations are solved on these three-dimensional grids, but with grid spacings, grid sizes on the scale of 30 kilometers, 50 kilometers, 70 kilometers, 100 kilometers, even with the world's most powerful computers. And again, this leads us to this issue of how do we incorporate sub-grid scale processes? How do we link the scales in the system? And so the sea ice components of these GCMs, or general circulation models, or global climate models. So here I'm just going to list and briefly mention some of the governing equations and some of the key things that people that create these big models, what they focus on. So one of the most important, I would say, there's been an awful lot of thought about, but it's maybe not so well understood, probably the least understood, is the so-called ice thickness distribution evolution equation. So G, what that means is the probability of finding ice of thickness h at time t at the position xy on the Earth. And it's this nonlinear PDE that has all the different ways in which you can increase the thickness, growth, lateral melting, and divergence, and so on. But one of the most interesting and least understood that I'm going to say is there's been an interesting development in that area is this mechanical redistribution term. I've certainly experienced this myself very much. I've been stuck in Antarctica a few times where basically you're in very thin ice. It's maybe 50 centimeters thick or a meter thick, but it gets crunched up against the shore. So the next thing you know, you're in ice that's 20 meters. You're in 20 meters of ice and you can't move. And that happened to us the last time. We were basically stuck for almost 3 weeks. It was pretty. Anyway, you wonder if you're going to get back or if you're going to run out of food or whatever. So, okay, and then this is basically F equals ma for sea ice. Coriolis effect, the drag to the atmosphere, the drag to the ocean, sea surface tilt, and then all the internal dynamics of the flows interacting with each other. And then we want to couple the temperature field of the atmosphere to the temperature field of the ocean through the sea ice. And if you didn't have this fascinating porous microstructure, it would just be a diffusion equation. However, it's really an advection diffusion equation because we can have fluid flow, convective fluid cells moving and turbulent flow within the sea ice itself. And we have some brand new results on that I'll mention towards the end. I'm talking of the flow of brine within the sea ice. So like on this scale, brine convection cells within the bottom portion of the sea ice. And that turns out to be really important because that brings up the nutrients for all the little critters that live in there, the algae and so on, but also it helps for heat exchange and so on. And I'll have some rigorous results about that towards the end. Yeah, it's an extremely complicated system with heights all over the place, and so it doesn't make sense to talk about a specific height. I mean, so you would want to talk about the probability distribution of finding particular heights, and this goes back about 25, 40 years. If you guys have any great ideas, the sea ice world is all ears. Okay, when I said one of the this mechanical redistribution term. So some of you may know John Wetlaufer. I've known him for many years, and he came up with a really interesting idea to transform the ice thickness distribution equation to a Fokker-Planck type equation, a Boltzmann type framework, where the thickness h, so this might itself is a diffusion process with that probability density. And the idea is that these, quote, microscopic mechanical processes that influence the distributions, these smaller scale processes, rafting, ridge, and open water formation, they occur on very rapid time scales compared to geophysical scale changes in this key function. And so you get a Fokker-Planck equation for that guy, and then this is, I think, what Henk was, if you put dt on both sides, that's almost what looking very similar to what Henk was discussing this morning, that form. Okay, let's focus a little bit on the microphysics and fluid flow through the sea ice. So fluid flowing through the porous microstructure of sea ice, it's not only important for climatological processes, but also ecological processes as well. Here are, say, the melt ponds, and whether or not, again, these ponds are absolutely critical because they determine the albedo or the reflectance of the sea ice. And as I'm sure many of you know, these low order, the simplest energy balance models for trying to derive an equilibrium temperature for the planet Earth, the single most important parameter that goes in there is the albedo of the Earth. And so anyway, these ponds are very important, and the albedo of the sea ice is very important. And whether or not those ponds grow or drain overnight, completely changing the albedo, depends on the fluid permeability or how easy it is for fluid to flow through that porous microstructure. This is a key parameter. As I mentioned before, the algae, these are the most robust algal communities in the world in some sense, in that they the food webs in the Arctic and the Antarctic and the polar oceans are, to my at least I've heard, they're the most sort of extensive and robust in the world, and these are the things that really at the base of this complex food web, the algae that live inside the brine inclusions. And also another really interesting process that actually led me to some of these key results that I'll talk about was being out on the ice in 1994, and all of a sudden, it was about midnight, a massive storm, and seawater all of a sudden is percolating up and flooding the surface. And this is a very important process in that you flood the surface, and now you have this slushy mix, and then it freezes. And about a quarter of the ice that's produced in the Antarctic is produced through this flooding and snow ice formation process, which again depends on the fluid permeability of the ice. So just a cartoon of the ecosystem, at least in the Antarctic. The killer whales eating the emperor penguins, and then the emperor penguins feeding on the krill, and the krill subsisting off of the algae that lives there. So it's a nice connection. Okay, so let's focus a little bit on the fluid permeability of a porous medium. This is a hunk of porous concrete. I really like this picture. The question is how much water gets through the sample per unit time. And again, this is our first example of homogenization. Namely, in general, this is the mathematics for analyzing the effective behavior of a complex heterogeneous system. And so a little bit of the math behind some of this. So it goes back quite a ways. You start with the Stokes equations for the fluid velocity, pressure, and force on a scale epsilon. And the whole idea is to step back, take an infinite volume limit, or take an equivalent scaling as epsilon goes to 0, and then derive the macroscopic equations, which are then Darcy's law and a divergence-free sort of an average fluid velocity field, along with an effective fluid permeability tensor. And so again, this is Darcy's law, where the average fluid velocity is related to the pressure gradient. The denominator is the viscosity. The bigger, the more viscous the water is, and this can be affected dramatically by the presence of algae. They secrete this really highly viscous stuff that I'll talk about in a little bit. But then we're interested mostly in this fluid permeability tensor, and it's a tensor because you have very different ability to pass fluid in the different directions in sea ice. It's the microstructure is highly anisotropic. Okay, so I spent a lot of time as a PhD student and in subsequent years deriving rigorous bounds on effective transport coefficients for composites. And so when we started to turn toward this problem, we thought, oh, this should be pretty easy. But then it turns out that getting the simplest bounds in the electrical case that were derived literally in 1912, like over 100 years ago, this is a much more difficult problem. You ask the question, okay, well, how do you arrange the microstructure, the pores, in order to maximize the fluid permeability in the vertical direction? And this is an analog, as I said, of the arithmetic mean upper bound for effective conductivity, derived originally by Wiener, but there's all kinds of variational approaches and other approaches to get those results. And so here is our rigorous bound in terms of the moments of the sizes of the inclusions, and they capture the data surprisingly well, this log normal pipe bound. The proof is very difficult. In other words, you can't just do it directly. You have to analyze, do a variation, or at least by this approach. We have a totally new approach now, but we have the first non-variational approach now. But basically through a variational analysis of the so-called trapping constant for a diffusion process in a pore space with absorbing boundary conditions on this, the trapping constant, and then there's a rigorous bound derived by a friend of mine, Sal Torquato, a number of years ago, that gets you the bound on the fluid permeability. Okay, now one of certainly one of the most exciting things that I've discovered in my career has been effectively what I would call the on-off switch for fluid flow in sea ice. And so roughly speaking, for brine volume fractions below about 5%, the sea ice is effectively impermeable. And then for brine volume fractions above 5%, it's permeable, and increasingly so for increasing temperature or brine volume fraction. And so kind of by a coincidence, by a certain rule called a certain law called the Frankenstein-Garner relation that gives you the brine volume fraction as a function of temperature and salinity, this critical value of 5% for classic congelation columnar ice. That I have to say that because we have another result for so-called granular ice. And this 5% corresponds to a critical temperature of -5 Celsius for a typical bulk salinity of 5 parts per thousand. Hence, it's become known as the rule of fives. Sorry, what? Okay, I mean you have a solid hunk of ice, and so what I mean is if it's 5%, that means 5% of that volume is occupied by the fluid inclusions. Yeah, that's the brine is salty water. Yeah, and it's relatively low. I mean, these volume fractions are pretty low. You know, for anyway. So this is actually showing how dramatic this rule of fives can control biological activity. So this is an algal bloom that just got shut down, and that basically that 2-day period is where the critical isotherm below which you're permeable, above which you're impermeable, passed through the algae, the layer where the algae was living. So it's rather dramatic, the effect that this rule of fives can have even on the biology. So why is this rule of fives true? Well, it's a percolation threshold. I realized that on the ice in 1994. I realized that out on the ice. It took many, many years to finally confirm all this picture that I had, but it's true. And here we start, say, a two-dimensional square lattice. A bond is open, the black ones, with probability P, closed with probability 1 minus P. This is about a third of them are filled. This is an impermeable state. Here's a permeable state where there exists an infinite cluster in this infinite lattice. And then the smallest value of P, of the probability for which you have the appearance of an infinite cluster, that is called the percolation threshold, which is exactly 50% in 2 dimensions. So now you might be wondering, well, and then well, what's the 3-dimensional version? It's about 30%. So how in the world do you get a threshold down about 5% for sea ice? Why is it so low? Oh, no. I just mean you're starting with an infinite lattice, and then just the percolation threshold is the smallest P when you just have an infinite connected cluster of the open bonds. That's what I mean. And it's very sensitive to the details of the lattice, these percolation thresholds, basically. There's much more interesting universal features of the system that I'll talk about. For example, the critical exponents that describe the behavior of the key parameters of the system near the threshold. The scale of connectedness, the correlation length. This is known in 2 dimensions. It's 4/3, been proven. Basically, then the exponent that describes the takeoff of the infinite cluster density, similar to the magnetization critical exponent for an Ising model. And what we're interested in here is the effective conductivity or fluid permeability taking off above the threshold, and that has an exponent T for conductivity and E for permeability. However, for lattice problems, they're the same. And I did a lot of earlier work in my career on, for at least in certain idealized models, actually proving rigorous bounds on these critical exponents there. Okay, so the key idea in understanding why the sea ice has such a low percolation threshold is in this, just basically based on this picture here. And so so this is sea ice. You have the brine inclusions are not just randomly distributed. They live kind of on the boundaries of these pure ice platelets. And this reminded me of a microstructure I had seen previously, a so-called compressed powder microstructure, big polymer spheres and little metal or carbon black particles. And you want the whole thing to be conducting, but in particular, you want this material to be radar absorbing. But you can achieve conductivity and the radar absorbing characteristics with very low volume fractions through this excluded volume effect. And all I did was I took the continuum percolation model that was developed for these compressed powders, applied it to sea ice, out pops the 5%. What's so interesting here is that these materials are so-called stealthy radar absorbing composites that they coat these aircraft with to make them invisible to radar. And as a result, sea ice itself is a radar absorbing composite. And I've heard the term holy grail so many times. The holy grail of sea ice is to get the thickness. So radar waves from microwaves from satellites get absorbed because it's radar absorbing. And so you have to think up all these independent ways, unusual and clever ways of actually getting a global picture of the thickness of sea ice. It's not easy. It's harder than you'd think. Oh, yeah, yeah. Basically, if you had just little individual metal particles disconnected in an insulating host, you wouldn't have much conductivity. But when they connect up, when they form, electrical pathways, that's what changes everything, and that's what percolation threshold, and you see all kinds of interesting behavior in the, say, the complex permittivity or the conductivity of such a material. Oh, no, no, it's the salty fluid. That's what's doing it. If it was, you have, they can measure the thickness of these, these 3 kilometer things, sending waves down that do not get as, certainly not, it's not as not nearly as absorptive as the sea ice is. That's for sure. Okay, so the next big step was to figure out, well, how does the fluid permeability depend on the brine volume fraction? And so we derived a set of rigorous, this is a kind of a extensive paper in the sense it was just a letter, but there was a lot of stuff in there. Rigorous bounds, percolation theory, a whole different kinds of models, network models, hierarchical models, comparison to field data of the fluid permeability that I'll just mention one of our percolation theoretic results. But what we also developed was finally an X-ray tomography method for analyzing the brine phase in sea ice. Previously, people had taken photos and tried to reconstruct the picture and so on, but we developed this mathematical X-ray tomography method where we could then analyze all the data and we can, do a 3-dimensional model of the brine phase. And I like to view this cover as homogenization in action. This is about a Can you guys hear? Oh, there we go. Yep, you can hear me. Okay. Okay. And so what was important about this X-ray tomography, we could finally start to confirm this rule of fives, that there really is a percolation threshold at this critical brine volume fraction. Here's some of our X-ray tomography. No pathways, one pathway, many pathways. We map 3D images of pores and throats onto 3D graphs of nodes and edges and use so-called finite size scaling techniques in physics to actually confirm this rule of five and really get our hands on the percolation threshold. Sweeping a lot of lattice and continuum percolation theory under the rug. This is a deceptively simple formula for the vertical component of the fluid permeability in columnar sea ice. There's the 5% where it takes off. This is the best known estimate for the critical exponent, and my upper bound was 2. So it's kind of interesting that my upper bound seems to coincide with the best known numerical estimates of the value of this critical exponent in 3 dimensions. And this is not a fudge factor, this K naught. It actually comes from critical path analysis. Developed originally in the context of electronic hopping conduction and doped semiconductors. And so we actually compute that thing from the X-ray tomography, and then you see how well the theory correlates. At least this version of the theory correlates with data. As I mentioned before, sea ice algae secrete this goopy sort of algal mucus stuff, extracellular polymeric substance, EPS, which then affects the evolution of the brine microstructure. Here's the brine microstructure without EPS, and then it starts becoming all fractally and all sorts of interesting. It sort of screws up the way that salt moves in and out of the boundary between the ocean and the ice. And so we go from a classic log normal distribution for the regular brine inclusions in sea ice to a so-called bimodal log normal distribution. And so then we've developed a random pipe network and then choose the pipe sizes from this bimodal log normal distribution, and we can then see an observed drop in the fluid permeability. And not only that, we can actually get new rigorous bounds based on this bimodal. I was a little surprised we could actually work all that out. And fundamentally, the question here is, how is the biology affecting the physics in this case? Yeah. What A was? Where are you looking? For brine inclusions? Oh, in the figure. Oh, I'm sorry. I'm sorry. I thought you were looking at it's the cross-sectional area. Okay. All right, now turning the page, and I'm kind of laying the groundwork for some of our new approaches to the advection diffusion problem that I think some of you here are certainly interested in. But the way we come at this is through stuff that I've spent a lot of time, a good chunk of my career, looking at the remote sensing problem for sea ice, and in particular, trying to get your hands on the effective complex permittivity of the ice as a two-phase composite. We'd be interested in reconstructing brine volume fraction, brine inclusion connectivity, of course, as well as the ice thickness and ice concentration, which are some slightly different problems. And so the quasi-static formulation of Maxwell's equation, so this is long wavelength, where the wavelength is very long compared to the microscale, to the scale of the inclusions. So here's the basic constitutive law that the displacement field is the permittivity, complex permittivity times the electric field, divergence-free, curl-free, and so on. And this defines the effective complex permittivity in terms of, that's the macroscopic version of that local law. And then the effective complex permittivity is a complicated function of the ratio of the component permittivities of the brine and the ice, as well as the composite geometry. And then a very powerful method that I got involved with my first year of graduate school at Karate with George Papanikolaou was the so-called analytic continuation method. Very beautiful mathematics where all the geometry information is contained in the spectral measure of a self-adjoint operator that I'm going to mention in a second. And then you get integral representations for the effective complex permittivity. That's it right there. This function f of s is analytic off the interval 0, 1 and the s plane, where s basically just involves the component parameters. And then we're also interested in inverting this whole process, where you're given bulk information about the composite and you want to invert for the spectral measure, which contains all of the geometrical information about the composite. Here's again just repeating this, and one of the key aspects here is that all the parameter information, this is what makes the method so powerful, all the parameter information is in that complex variable, and all the geometry of the composite is in the spectral measure. And this spectral measure is associated with a self-adjoint operator gamma chi, or chi gamma chi, depending on how we formulate it. Gamma is projection onto curl-free fields, gradient, inverse Laplacian divergence, and the randomness, that's non-random. All the randomness comes in through the chi, the characteristic function of the brine phase, 1 in the brine, 0 in the ice, or 1 in the melt ponds, 0 in the snow, and so on, for a two-phase material. The mass of the measure is the volume fraction of the brine, and the higher moments depend on endpoint correlation functions. And what really makes the method go is this very beautiful resolvent representation for the local field in the problem, in this case the electric field, and you see in terms of that operator. So everything can be expressed in terms of this basic operator. We've done a lot of work on using that integral representation to get rigorous bounds in the complex plane on the effective complex permittivity. Here's some very tight bounds under this so-called matrix particle assumption, where you assume that the brine is really in separated inclusions. And this is inversions here, where we actually can see how the brine inclusions literally start to coalesce and get closer and closer as the temperature is increasing. But again, this is all done electromagnetically. Yeah. Well, not really flow per se. This is just a stationary, solid ice with brine inclusions. Yes. Oh, no. This is being applied This is being applied. We've done all kinds of experiments. We have all kinds of ways of sending electromagnetic fields through the ice. Yeah. So that's the setup that we're interested in here. Okay, a great example of cross-pollination. So we developed all these methods for characterizing the connectivity of the brine microstructure in the sea ice, and then fortunately, the math couldn't care less if that porous microstructure is in human bone or sea ice. And so we've applied this spectral measure analysis to developing a new method of electromagnetic monitoring osteoporosis in human bone. Here's good healthy bone, here's more older osteoporotic bone, here's the spectral measures directly calculated here. You see that this goes up to 3, that only goes up to 1, so the mass of this is much less in the older osteoporotic bone. And then this is the inversion scheme, is actually taking complex permittivity data and then reconstructing the spectral measure showing the difference between the young healthy bone and the older osteoporotic bone. Yes? Oh, no, okay. I mean, we're basically, we're just analyzing the quality of the connections, the connectivity of the phases. Yes, it's true that that as brine flows through the sea ice, it can change the microstructure, as you're saying. However, we're not, we're imagining just a stationary situation, and we're taking the methods that we develop for sea ice to characterize the connectivity of the brine phase and apply that to bone. Well, it's just, okay, if you just have a hunk of sea ice that's just sitting there over an hour, I mean, the brine is not necessarily moving around, especially if it's very cold. It can be completely stationary for reasonable periods of time. Okay. All right, so this spectral measure, that's the key object that we're really interested in. And if you discretize, say, an image of a composite microstructure, it gives you a lattice of ones and zeros, a random resistor network. And then this fundamental operator, chi gamma chi or gamma chi, depending on the formulation, becomes a random matrix, which depends only on the composite geometry. So we have a random matrix, and then we can compute its eigenvalues and eigenvectors, and then from those we can actually directly construct this spectral measure. There have been some earlier studies of trying to do this in a more clever way, and I call ours kind of the dumb way. In other words, we're just doing it so directly. However, that opened up a whole new world that we didn't expect, that I'll tell you about in a couple minutes. Okay, so here's just sort of the continuum case and the equations going through, and then here's the discrete versions of these underlying equations and formulas over there. And so now we start to get into some of the results in this case. These are just computations of the electric field in resistor networks as we keep increasing the volume fraction. And so these are the examples of the spectral measures in these cases that you can then plug into the measure and get exact representations for the effective parameter. However, because we did the dumb calculation and directly calculated the eigenvalues and eigenvectors, we can then analyze the statistics of the eigenvalues. And so what we found is in very low volume fraction, when the, say the brine inclusions or whatever are all disconnected, you basically have uncorrelated eigenvalues, or their spacings are uncorrelated. But then as you develop long range order in the system and you start to approach this percolation threshold, then we approach the distribution of the eigenvalue spacings approaches these so-called very famous Wigner-Dyson universal distributions, in this particular case known as the Gaussian orthogonal ensemble distribution. And this sort of led us unexpectedly into the world of random matrix theory, developed by Wigner and Dyson, first used to study the very high number of quantized energy levels in a heavy atomic nuclei. And you have Gaussian orthogonal ensemble, Gaussian unitary ensemble based on the matrices. Although you typically in random matrix theory, you have like, oh, the entries are just chosen from some distribution. We have a very different situation where it's the underlying geometry that determines in a complicated way what the elements of this matrix are. By the way, for you pure mathematicians out there, the biggest unsolved problem in mathematics is, I guess, the zeros of the Riemann zeta function, and they obey that one of these universal Wigner-Dyson distributions, interestingly. And we find it in melt ponds. Go figure. So here's some melt pond images. Here's our calculations of the spectral measure, uncorrelated eigenvalues, and then transitioning to this famous Wigner-Dyson and the fact that it goes to 0 there, that means that the eigenvalues they're repelling each other. They're correlated. And we finally realized this is just a piece of a much larger, fascinating picture that we discovered. Basically, we're seeing all the hallmarks of the so-called Anderson transition, which has been discovered in wave physics and that Anderson got the Nobel Prize for understanding the metal insulator transition. But we're seeing it in systems that don't involve waves, which is I find fascinating. So the basic picture there is you have low disorder, extended wave functions for electrons, and then basically eigen energy levels that communicate with each other because the electrons are seeing each other. But then you raise the disorder, they become localized, and you go to Poisson distributed energy levels. And we see that's the picture that we're seeing. As we approach the percolation transition, we see this transition to universal eigenvalue statistics. We see extended states and mobility edges that you see in condensed matter physics. But again, without wave interference. This all works for just thermal conductivity, diffusivity, quasi-static limit of waves, but again, no, there's no scattering effects or anything like that. So we find this quite fascinating. This was just published in Physio Letters back in January. Here's a bit of the localization issues. Eigenvector localization and mobility edges measured by the so-called inverse participation ratio. This is kind of what mobility edges. This is extended states localized at these edges, and we see this same kind of behavior in melt, the behavior of these spectra for melt ponds, for the brine phase, and just for these random resistor networks as well. And we see a transition to delocalization as we approach this percolation threshold. Okay, there's a whole nother problem now where we can do homogenization. I had a PhD student finish a few years ago, and we worked on this to basically extend this very powerful analytic continuation method to the polycrystalline problem. Namely where we might know the statistics of the individual crystals and their distribution of their angles, their orientations in the sea ice. And then we were able to derive these Stieltjes integral representations for the complex permittivity, derive forward and inverse bounds, and then develop by what I call a two-scale homogenization method as to derive the bounds on the effective complex permittivity, but then also to invert all that to get basically to give a new method for distinguishing between columnar ice, which is very different in granular structure, and so-called granular ice that dominates in the Antarctic, which have very different fluid flow properties. So we're really interested in being able to electromagnetically distinguish between these two ice types. It really affects the biology a lot. Ecologists are really interested in this distinction, particularly Antarctic people. The two-scale homogenization process, here's an individual crystal. We numerically figure out the effective complex permittivity tensor for one individual crystal, and then we have information about the statistics, and then we analytically derive these very tight bounds on the complex permittivity, given information about the orientation statistics. Okay, now it looks like I'm completely turning the page, but it's going to be the same methods. This is the advection diffusion problem, plays a key role in the transport of sea ice and in atmospheric and oceanic flows, like that first picture I showed you. But a lot of other problems, of course, that have been talked about this morning. We're interested in advection enhanced diffusion. In particular, we're interested in the effective diffusivity. Tracers, buoys diffusing in ocean eddies, diffusion of pollutants in the atmosphere, salt and heat transport in the ocean. And one of the things that we're specifically interested in is heat transport through sea ice in the presence of a convective flow field. So here's the advection diffusion equation, and then it's homogenized for where you have that effective diffusion coefficient that incorporates the effect of the velocity field. And so the original work was done on this to try to get a Stieltjes representation for the effective diffusivity by Andy Maida and Marco Avellaneda many years ago. And what Andy and Marco did was to adapt the functional analytic framework that George Papanikolaou and I developed, and they adapted it. It goes from a self-adjoint operator to a skew-adjoint operator with its eigenvalues along the imaginary axis, and that was basically their initial foray into this direction. And then we've really taken up the mantle in the last few years and trying to really analyze these spectral measures. How do you compute these things? How to lay the mathematical groundwork for doing all that. This is the advection diffusion equation here. We kind of put it in the framework of this, where this is like an electric field. it's a very similar framework to what we did in the electrical case. And again, this is the Stiltjes representation for the effective advection enhanced diffusivity. All the geometry all the flow information is buried in the spectral measure, and that's the local diffusivity. And then we've applied this. Well, actually, first of all, now we can also compute the eigenvalues of this analog of the operator. So now the eigenvalues depend on the geometry of the flow field. And again, for this cat's eye flow, we see this amazing result of, well, this GOE, Gaussian orthogonal ensemble, appears again. And so we're really starting to look into some of these mathematical aspects here associated with this. And so the problem of convection-enhanced thermal conductivity of sea ice, the measurements are really hard to do. There's no theory that I know of. And we have the first rigorous bounds now on the effective thermal conductivity in the presence of a flow field as a function, say, of the strength of the field, or the strength of the velocity field. Okay. Now, turning the page. Okay, now I want to show you just a tiny bit of video. Okay, and let's turn up the. Can we get this? Where did Freddie go? Oh, we need the sound. Just turn up the sound a little bit. Okay. Okay, I think that's okay. So this is some of my video, and there's also another video showing waves propagating through the sea ice pack, which I just find absolutely fascinating. Okay. So it's got to be turned up some. Okay. So you see this beautiful, and this is the quasi-static limit. You see the scale of the little inclusions, and the wavelength is much longer in these kind of situations. And that's the Aurora Australis there. My first exposure to this was in 1994, about midnight, 2 in the morning, where we're entering the ice pack, and I was on watch then. This is from our 2012 expedition to show you locally kind of what it's like. Here you see the entire sea ice scape undulating, which I find. This is my first exposure to this. This is my first video of this, but you see just how amazing. It's one of the most hypnotic phenomena I've ever seen. I've had like almost terabytes of video of this stuff. And this is not my video. This is from the Polar Stern. So this is a German video, but it kind of shows you what it can be like. And again, we have, in the quasi-static regime, the long wavelength compared. Check this out. This is amazing. I just live for this stuff. I don't know what it is, but the Germans put this together. And there we go. Okay. All right. Okay. All right, and so the person who was Alice and Cahoot, they got a beautiful paper in Nature. Basically, that's actually me taking a photo of them deploying their instruments onto an ice floe to get the wave data. And during 3 large wave experiments, the significant wave heights did not decay exponentially, which allowed the waves to propagate much further into the pack than people had ever expected. And then also they found this amazing correlation between ice extent and significant wave height. Yes. Oh, okay. All right. So, all right, so we have, there's various models for this. What we're interested in is the complex viscoelasticity. That's like the water version of the complex effective permittivity. We've now derived Stiltjes integral representation. I believe it's the first rigorous results in this kind of, in the wave, at least in this wave field. And so the Christian Sampson is a PhD student of mine that just finished, and I'll just skip. We have this beautiful. Again, we're able to manipulate the equations to get this beautiful resolvent formula for the strain field, and then this same kind of Stiltjes integral representation in that case. And these are the rigorous bounds, and we have ways of getting them much tighter. But again, these are the first rigorous results that I know of on this kind of propagation problem. We've also been looking at, with Court Strong, using some really interesting ideas, these simple ideas of solving Laplace's equation to get our hands on where the waves propagate, which is the marginal isone, and what's the width of that object? Well, a court came up with this really cool idea where he averages the lengths of streamlines, and we've analyzed, and that's actually the where a similar method for measuring the thickness of the cerebral cortex of a rat brain. Same problem. And anyway, we've done a lot of analysis on these types of things, and also we've used that to fill. There's a classic problem of the polar data gap because of the way satellites work, and you get these holes. And we've then used Laplace's equation and as well as stochastic terms to fill in this hole with seemingly excellent results. And it was just published in Remote Sensing a little while ago. So then finally, some of the experiments we've been doing, we have a large array of experiments measuring the electromagnetic and fluid transport properties, both in the Arctic and the Antarctic, particularly recently. This is the cover, the notice is the AMS. Here I'm doing the first measurements of fluid permeability in the Antarctic ice pack, and they look like they're doing really heavy experiments, but in fact, they're playing soccer. This is the columnar ice versus granular. We have finally nailed down the fact that there's a higher, it's not the 5% threshold. This took many years to get this, to finally be in the right place at the right time with the right equipment to get that. Here's some of my tracer experiments that we use to analyze various things. I'll show you just one at the end. And the very last thing I want to just mention about is these melt ponds and the fantastic fractal and multi-scale structure that we've been looking at. And so again, these melt ponds are major drivers in polar climate and one of the most important components of the sea ice system. There's a lot of very detailed models that use our permeability results and so on. But as an ex-statistical physicist, I wanted to step back and ask more general questions about this. And so the first big result we had here was we discovered a transition in the fractal geometry. This is log variables. The slope is the fractal dimension. And as soon as I saw this, I got so excited because there's obviously a transition in the fractal dimension. That, a simple Euclidean pond, that's a transitional pond. He's trying to become self-similar. And this is a fully developed complex pond with a boundary that's behaving like a space-filling curve of fractal dimension 2. Here's a graph of our real data for real melt ponds showing the transition centered around a central critical point of around 100 square meters, where the center of the transition regime and fractal dimension. There's a percolation threshold. We're doing all kinds of work right now, actually with these amazing high school students, on what's the percolation threshold, the correlation length critical exponent, and so on. We think it's the same as the universal lattice value. We're just about to publish, or it's already been accepted in the Journal of Fractal Geometry, a model that comes out of plasma physics actually, where you have a random surface and then just a plane that moves up and down, and you get these pictures, and we can really study the details of that fractal transition. Another problem here is, well, you have these large drainage patterns, that's like a seal hole, and water's being drained out of there, and that can, again, change the albedo dramatically. And so we've developed algorithms to map these images onto random resistor networks and then analyze those resistor networks to look at the effective horizontal fluid flow properties of the ice pack itself. And then finally, and I'm not showing any details here, but probably the model that we're most excited about is an Ising model. So this is the most widely studied model in statistical physics for phase transitions. So instead of spin up and spin down in an external magnetic field, we consider water and ice as the two spin up and spin down. And then amazingly, and again with very little input of physical parameters, just let this model go, use Glauber dynamics and minimize energy, we are able to then directly predict that transition in the fractal dimension within 20 meters. We get the correct for the transition. We also can, the function, the fractal dimension as a function of area, we get that. And then even more importantly, there's an iconic exponent that's been around for about 20 years, characterizing the pond size distribution function. What's the probability of finding a pond of a particular size? And there's an exponent of -1.5 that describes the fall off of that function, and we predict about -1.56 or something like that. It's amazingly close given what a low order model this is. We're very happy with this. I think we're submitting the paper tomorrow. Okay. Finally, there's the last thing is, so I was on this great expedition to look at under ice algae blooms and melt ponds back in 2014. But Chris Polishensky, the moment we got out there with my permeability equipment, the idea is you drill a partial hole and watch, and then basically you want to measure the rate at which the water fills the hole back in. within literally a half a second of drilling the hole, it's filled back in. So the sea ice is so permeable. So then this begs the question, well, how in the world does meltwater sit on top of the ice without draining? And we figured this out. It's a conundrum, but basically what we came up with through lots of experiments and dyes and changing salinities and so on is that the snow, it's fresh water. Its freezing point is 0 Celsius. The ice might be, the freezing point for seawater is like minus 1.8 Celsius, but the ice around there was about minus 1 Celsius. So this fresh water starts percolating down through the porous microstructure, hits this slightly colder through the porous matrix, and it freezes up. And so it dramatically, the permeability falls off, it blocks up the pores, and you hold water, and that's how melt ponds are formed. So in conclusion then, the summer Arctic sea ice is melting rapidly, and these melt ponds and other processes must be accounted for in order to ultimately try to capture the correct rates of melting and what's going to happen to the ice pack. Fluid flow through sea ice mediates melt pond evolution and a lot of other these critical processes in both the climatology and biology of sea ice. And in particular, we've been using methods of homogenization and statistical physics, which provides a natural framework, a natural set of ideas to link scales and provide rigorous methods for finding effective behavior and ultimately advancing how we treat sea ice in climate models. And then critical behavior in many different forms is just a natural part of the climate system. From my point of view, as somebody who actually goes to Antarctica and the Arctic, I think that field experiments are essential to developing relevant mathematics. And then finally, we hope that this research will help improve projections of climate change and ultimately the fate of the Earth's ice packs and the ecosystems they support. And thanks to NSF and to ONR for supporting all this research. So, sorry, related to what? To melt ponds, yeah. Yes. Yeah, basically the interaction, we basically just tell the system how to keep updating, and basically depending on, there's a topography that goes in there, and depending on where the water level is compared to the topography, in other words, and we have these specific simple rules that tell you how to update the system, and then you go by Glauber dynamics. You want to minimize this, keep minimizing this energy, and and then these melt ponds are viewed really as metastable states that are converged too, as you progress through the Glauber dynamics. Yeah.
How does the topography affect whether it's ice or water?
Well, the topography's changing. That's because it'll melt. That's what happens. That's how you develop the melt ponds and how they evolve and everything. But that's amazing. What's amazing to me is going from complete disorder to order out of this easing model. You start just completely random, and then you just let the system go to minimize energy, and it goes to the right thing. It goes to these configurations that have the exact geometrical characteristics of the ponds that we observe. It's, again, it's quite striking to me. And yeah. Yes, that's a key process. Daniela Flacco and Danny Feltham at my friends and colleagues at Reading, they're doing some work on refreezing and how that all plays a role in some of these things. We haven't really considered that too much though in our work. Yeah. Yes, so it's like a layer, like a 2-layer medium. There's water, and then there's a layer of ice. Possibly, as I said, we're really in this. We've done what we had to do, still, with reasonable steps to manipulate the equations into this beautiful form that we can get the resolvent represent and these integral representations for the effective complex viscoelasticity. So there are certain things that we have not considered. But this has become an extremely active area in sea ice research, partly because the Arctic is opening up. So there's much more. The marginal ice zone's much wider now, and there's just much more wave activity even in the Arctic now. So we have not incorporated every physical effect, but the kinds of things you're talking about, there are people that do all kinds of detailed experiments and all kinds of analyses and try to incorporate these things. So. That's interesting. I don't know. I don't know.
A lot of fascinating results. Not quite sure I've reached my personal percolation threshold for all of them to sink in. Maybe you can help me. You mentioned the climate modeling part a few times. Let me just focus on this. Can you maybe give a few guideposts posts of where concretely your results help me or help other
Okay.
guys?
I can.
Guys,
Yes.
you mentioned some of the ingress problems, what you would need to measure to make these parameterizations better, and how your results help you using the measurements more effectively.
Oh, okay. So one specific uh, one specific result is our fluid permeability results. Um, in other words, that's kind of, I guess, the standard now for the fluid permeability as a function of brine volume fraction or temperature, and those, so that, and again, that determines the drainage of the ponds. And so those our results there have been specifically incorporated into new melt pond parameterizations that are incorporated into the Los Alamos sea ice model.
So how do you predict phi, for example, in those CS models then
As
historically?
of okay, it's specifically as if, when you know the temperature and the salinity, which is part of the parameters that go into the models, then you know the brine, and you immediately know the brine volume fraction. There's just a formula called the Frankenstein-Garner relation, which is at the heart of that rule of fives as to why they're all fives. Again, it's kind of a coincidence, but that's how it works. There's a lot of work trying to bring wave action into climate models and so on. There's a big ONR project that's been going on for a few years there, and we hope eventually some of our wave results could be incorporated there, given information about flows and so on. Although I'm not sure that these models are going to go down to that scale exactly, but anyway, yeah, yes, yes. Oh, that's an interesting question in the sense that basically pancakes only form in wave fields where there's winds, because it's basically this, they sort of bounce up again, they form little rims around the sides, and basically what's really how you start off with like what's called grease ice. So basically there's just all this tiny little individual crystals, um, and the surface of the ice looks like grease because all the really high frequency stuff is all damped out because of the viscosity of this conglomerate. But then but now if you're in a wave, they start to push together, apart, push together, and they start to really congeal into these little pancakes. Um, uh, I don't know the arguments that give you what you're asking. I think there probably are some scaling arguments, and I think there have been people that have thought about this, about the size of the pancakes based on wave speeds and wind speeds and wave lengths and so on. But I'm not too familiar with that myself. But
So at the beginning of your book, we are seeing data or models about the extent of the sea ice
yes,
core.
yes,
You have shown the discrepancy is very low,
yes,
but both the models and the observation had something like a sharp transition around 2000 or something,
yes.
2007. Why is there such a sharp transition?
That okay, I think I don't know too much about this. I know there were some issues back in 2007. There was some massive high pressure system that persisted for a long time in the summer. So the sun was just beating down. So the I think there was some, like, okay, is this really representative of what's really going on, or is it some large fluctuation? I think people started to believe things more in 2012 because I think that was a much more normal year, and now the ice extent was much less. But I do not know about specific transitions in these models in terms of trying to capture these relatively short-term types of features in the data set. I don't think I'm not it's not to, at least it's not clear to me that that's really been looked at or thought about really carefully, aside from trying to explain these extremely low levels that were seen in certain years based on meteorological types of conditions at the time.
I think
Okay,
so.
yeah.